Okay, I'm going to talk to you about LLVM and HPC, which is roughly what I do, like in a nutshell. And that can mean a lot of things, and it does mean a lot of things. And I'll try to give you some, overview over various topics. There will be a lot of OpenMP, just because that is where I spend most of my time, but that doesn't necessarily mean it's all OpenMP. I'm trying to give you a little bit of LLVM overview in the beginning. I'm trying to tell you a little bit of non-OpenMP LLVM things that we do, partially because we want to use them for OpenMP. I'm going to tell you like researchy things that we do and so on and so forth. And at the end of the day, what I hope to convince you is that working with LLVM is fun, working in upstream is an actual option for people, and that it has benefits to do so. Okay, let's take a look at this. I give the talks, and I sometimes give these talks, but there is like lots and lots of people that actually work on this. So there's everyone from academia, people that write papers and actually commit code, to industry people that we work with that commit code and that help us design stuff and so on, to power users that take our stuff and really, test it out with large codes and come back with performance results, with profiling information, with bug reports and so on. So there's a lot of people involved. So only me giving the talk here doesn't really mean anything. I was just in the neighborhood. So about me. So this is me at ETH, and I got my PhD in 2018 from Saarbrücken, and I used to work at Argonne for 4 years, and now I work at Livermore. As we said, LLVM community for by now almost a decade, and I'm active in the OpenMP Standards Committee and the code owner for LLVM OpenMP offloading officially since 21, unofficially a little bit longer. Let's talk about LLVM. I'm not sure what people know about LLVM, but I figured I'll give like a very brief intro. So LLVM is an open source compiler, an open community, and so on. So everything is really open. If you ever see, the LLVM calendar, Google Calendar, all those calls about alias analysis, machine learning, about the RISC-V backend, the SPIR-V backend, whatever there is, those are open. So you can just call in. You can just lurk there and just listen in. You can come in and ask questions. You can tell them they're all wrong. It's all fine. The forum is open, like our mailing list, our discourse, our IRC, everything is open. Feel free to join. It is extensible, which means it's fixable. So if there's something that it doesn't do well, which there's a lot. I mean, there's an arbitrary amount of things, right? You can go in and actually, fix it. And it's not that hard to do so. It's portable in the sense that you can use it to compile stuff for various CPUs and various GPUs. Not as portable as GCC is, but for most people, it's sufficient. It supports C++, new C++ features. It supports like OpenMP, a lot of the newest features, SQL, HIP, CUDA, all the C languages. We're working on Fortran support. You can use it when you deal with Rust. You can use it when you deal with Julia, and the list goes on. So you get all those languages. You get access to them. You get access to like really cool features in languages, in backends, and so on and so forth. It's obviously performant and correct all the time. I mean, what else would it be? And maybe interesting to people, it's the basis for all the vendor compilers nowadays. I mean, I said most, but effectively all, which means that if you change something in LLVM, it trickles down into the vendor compilers. Maybe you don't care about LLVM per se because you don't roll it out to your people, but you could roll out the vendor compilers. So you might want to fix it in LLVM or give LLVM a nudge in the right direction such that the vendor compilers take it. And when you deploy it, you get the good stuff, right? That's what we do. That's kind of our modus operandi. Even if we don't deploy LLVM ourselves and like LLVM Clang on our codes, we get the stuff we do back through the vendors. Okay, LLVM. So this is a screenshot of the LLVM repository. There's a lot in there. There is the C family front ends, everything that has that looks like C or quacks like C is supported by Clang. You get all the sanitizers, everything from thread, address, undefined behavior. We're working on a modern Fortran front end, like actually modern Fortran. It's in a better state than most people realize it is in. So there is a lot that works, and it actually doesn't work. That works pretty well, actually. A lot of things that don't work, but is in a better state than people realize. We have an own C++ standard library implementation that has, different trade-offs to lib standard C++. We have a fast linker that has a lot of features. We have an own debugger with different trade-offs to GDB. The core LLVM stuff, the middle end and the back end. So this is core LLVM oftentimes. And that is, one out of what, 20-ish different subfolders in the LLVM project. So this is our mono repository. So core LLVM is like one thing out of 20. The OpenMP runtimes all live in the OpenMP folder. This is host runtime, device runtime, GPU runtime, offloading stuff, all of it. Sorry. So there is a lot going on. I mean, I could go on through the others, but it doesn't. So LLVM. This was taken from a tutorial we gave years ago. You find it on YouTube. Generally speaking, you have a C file. You use Clang, C-lang, to compile a C file into LLVM intermediate representation, often LL files or BC files. Then you do optimizations on them, and everything stays in LLVM intermediate representation. So the tool to do that, if you do it standalone, is called opt. Then you use an assembler to get LLVM machine IR, and then you can do optimizations on LLVM machine IR again, and then you get into machine code, like actual machine code, object code. And what my work is, 80–90% in this part. There is a lot, or 80–90% in this part on LLVM core. Then there's a lot of work in the runtimes and so on. But I usually don't venture this in this area because it's scary. But people do, and I'm grateful that people do. Now, okay, I talk about LLVM. This is one of those slides that you might want to just take a screenshot of or like look back later. I'm not going to go through it. Nowadays, you can configure LLVM a single CMake command. You say, make or Ninja, and then you get an offload capable Clang compiler that can do CUDA, OpenMP offload, and whatnot. That's it. So it should be really simple. There is another cheat sheet here about what things to consider if you're, a new user. None of these is really surprising, and most of it actually holds for all other compilers as well. Not all compilers support like thin LTO, so that's kind of a differentiating feature. But more or less everything is, if you're a user and you're new, you might want to be interested in this. Otherwise, you probably not. Let's talk LLVM community. I said earlier, LLVM is like an open community, and there is a lot of ways to get in touch, and you really should. Like, oftentimes I go places and they're like, "Oh, we tried this, it didn't work," and I'm like, "Okay, did you ask anyone or report it?" And they're like, "No." There's two things wrong with this. First of all, if it really doesn't work, it won't change. Nobody knows you needed it. Nobody knows it doesn't work. Nobody knows anyone cares. So there's very little chance it's get fixed. And the second thing that might be even more interesting to the people is it might work and you just didn't, find out how. Why not ask someone? I mean, it's literally is a cost of what? 5 minutes to put an email out or put it into the forum. Worst case, they ignore you. I mean, come on. So we have Discourse, which is kind of a forum mailing list. Discord, which is a chat. IRC, that's where I hang out. There's a old school chat. We have weekly, bi-weekly, or all once a month meetup, sync ups where alias analysis, MLIR, machine learning, OpenMP, RISC-V, yada yada yada. A lot of people now have office hours, so you can call in once a week or so and just ask them stuff. And they will either help you or direct you towards other people that might be able to help you. So if you have no idea where to start, I have people calling my office hour and just like randomly bouncing up ideas or asking me like weird random stuff. It's fun and it's simple. If you want to know about all of these things, go to the Getting Involved page on the LLVM org, which is a very nice, web 1.0 web page. It's really good. And then you find all of these links, and then you can read up more on them. And we have a calendar and everything. It's all great. Okay, let's talk about a little bit of technical stuff here, right? Parallelism and LLVM. And while I'm going to show OpenMP here, at least in my motivating example, and I show it for LLVM, pretty much everything I say is going to be true for all kinds of parallelism, and it doesn't matter what model you use, whatever, it does really not matter at all. And it's probably going to be true for any compiler you've ever used. There might be very few exceptions, but last time I checked all the major compilers, all of this was true. That was not long ago. Let's take a look what a compiler does and what we expect a compiler to do. So we think a compiler should take this original program here and it should say, oh, y is 7, right? So I should replace y with 7 everywhere. That's what we think a compiler should do. And all of your favorite compilers will do that. It's great. It's great. It's all good. Now we're told we need to use parallelism because parallelism is important. So we are like, okay, OpenMP parallel 4. And now again, you can use TBB, pthreads. I don't care. Use whatever you want. CUDA for all intents and purposes. But nothing else changed. So we just made this parallel, right? So it's good, right? Turns out the compiler is not able anymore to replace this y with 7. Finally, it's not even able to replace this y with 7 after this parallel loop. At least not LLVM and most others. In this case, I can if you want to know why, I can tell you later. And there's ways around that. But long story short, using parallelism introduces indirections by design on purpose. And compilers so far were not really able to deal with those indirections. So adding parallelism effectively caused you to lose performance on your kind of single thread performance. And then you hope to make up with it by scaling. That was cool. So let's don't trust me. Let's look at some numbers, right? So earlier I complained about Rodinia benchmarks. So here are my Rodinia benchmark numbers. This is my baseline, which is just the benchmark run on a machine with 03 AMAX native, how long it takes. And this is my parallel baseline. So this is sequential code, just compile it, run it. Same compiler. And this time I enable OpenMP, which is in those benchmarks, like they have the OpenMP pragmas, right? And I enable OpenMP, and this time I say num threads 1. So it's also sequential, but OpenMP enabled. That looks bad. So I lose 40%, 140% of my performance when I enable OpenMP on a single threaded performance. That's kind of not good. Now it turns out if you teach a couple of analyses or transformations in LLVM about this indirection, and that this specific indirection is not as scary as it looks first. So you explicitly teach it about these things. You can get you teach the first pass about this attribute deduction, and then you teach the second pass about this, the argument promotion. Each in isolation doesn't actually give you anything, but after you taught both of them about it, you get performance of your OpenMP-enabled sequential execution on par with your sequential execution without OpenMP. So all of that indirection overhead goes away if you teach the compiler, hey, this is an indirection that has the following semantics, and then the compiler does what it would have done in the sequential code. I mean, that doesn't mean it always will work, but that means that there is work to be done and work can be done, right? Okay. And this was, 2018. So this was kind of when I started. When I started with the labs, I did a study. This was the very first thing I did because I wanted to know where we are, what's working, what is not working. And this was the result. So that's a lot of things came out of this. And I don't know why so much for my animations. So they were supposed to pop up, but anyway. So if you want to see more, go to YouTube and look up this talk. I'll talk about how LLVM solves this now. I'm not going too much detail into this today. Let's talk about LLVM OpenMP. LLVM OpenMP. If you say OpenMP, people think pragma-om, right? That's what the first thing people think. Maybe then they think lib-om or libgumb or whatever. But LLVM OpenMP, when I say that a lot, I mean a lot of different things because it's For one, there is all of this Clang parser, like the OpenMP parser, OpenMP semantic analysis, and OpenMP code generation in Clang. And then there is the host runtime, the classic stuff. So this deals with the pragma on. This is the classic host OpenMP runtime. But then there is the target, like the generic target offloading runtime. And then there is the GPU specific runtimes. Then you have another front end, and now you don't want to duplicate all of this stuff, especially not this part. So we like put that into an own component that you can now use from different front ends or even no front ends at all. So if you, for example, write a parallelizer, you could kind of opt into OpenMP parallelism without having pragma omp anywhere, which is kind of nice. So if you have a language that doesn't have pragmas, not a problem. You can still kind of, opt into the same thing through the OpenMP RR builder, which is just a way for you to write to generate the right code that corresponds to a omp parallel without having pragmas in the first place. And then there is this path that we worked on for a while now. It's called OpenMP opt. It's in our LLVM mainline, and it's enabled by default if you have OpenMP enabled. And it will do interprocedural optimizations that are kind of OpenMP specific to a large degree. It does host optimizations and device, like device is GPU optimizations. And especially on the GPU side, if it doesn't trigger, your performance oftentimes is really bad. If you want to learn more about LLVM OpenMP, there is a 3-hour tutorial on YouTube. You can, fast forward or increase the speed or whatever. But I mean, I'm biased, but it's probably interesting. All right, let's before we go into some details on into the weeds on some of those, things that we did and things that I want you to know you should do and whatever. Let's talk a little bit big picture directions, right? This is a rough sketch of mine. You look, it's beautiful, isn't it? It's me drawing the diagram of how OpenMP currently is compiled in the LLVM world. You have front end is OpenMP, so OpenMP on C and C++ in this case, right? It goes into Clang. It can also go into Clang. It's under development. A lot of stuff is working, not everything. And then Clang generates with the OpenMP IR builder and some of the old style code, LLVM IR with OpenMP runtime calls. Clang uses MLIR and then uses the OpenMP IR builder to generate the same thing. You do OpenMP aware optimizations, and then you target the OpenMP runtimes, which then target FPGAs, GPUs, CPUs, have a virtual GPU, the kernel JIT, profiler, debugger hooks, everything. So this is the entire ecosystem drawn in a little nice diagram. Okay. This is what I see happening in the future. Now you can agree, disagree. That's fine. It's one opinion, one potential possibility. That is, all of these input languages actually will be compiled down in the upstream LLVM at least onto the same representation here. Now, at this point, if this happens, or as this happens, we're probably going to get rid of the word OpenMP everywhere here, and we're just going to call it, accelerator or whatever, parallel or offloading or whatever. So we rebrand everything. But conceptually, it's the same thing, because right now, there's a lot of duplications from the languages we already support and how we support them, the libraries, and so on and so forth. And then we depend on various vendor tool chains to various degrees. And all of that is not great in terms of maintenance, in terms of interoperability, in terms of portability. In this picture here, and if you look at things like the blue arrows, right? Which I have research prototypes that exist. So you can, proof of concepts, you can use these things. You can port CUDA with Clang onto the OpenMP runtime. And then you can execute that on the host, or you can execute your CUDA code on an AMD GPU. And you can then also combine it with OpenMP offload. And you can combine it with OpenACC that goes through Clang into the same intermediate representation. So the whole thing, oh, you can't write your app in this language, or I write this part, we have to agree on a language, it's all syntax at some point. We normalize a lot of it already. I mean, most languages go to LLVM IR eventually with different runtime calls. Why not, agree on the runtime calls and call it a day?
Maybe a question. So maybe a question I'm not aware of. There is this arrow into Clang. So what does that mean? Does that mean you are doing kind of source to source code transformation, or do you hook into Clang itself? So in other words, do you generate C code and Fortran code, and then the compiler does something with it? Or is it really then an OpenMP specific code generator? And maybe related to that, when the chain goes on to the runtimes, the runtimes, at least in my understanding, are kind of a library.
Yeah.
And so how much code is generated, really code generated, and how much is just calling routines in the runtime?
All right, let's start with the first one. For all arrows that go into Clang and the arrows that go into Clang, those language extensions for OpenMP and OpenACC. So OpenMP is always OpenMP and C, OpenMP and C++, OpenMP and Fortran, and for OpenACC the same thing. For those arrows, Clang and Clang are potentially, with some research prototype extensions, actual compilers for those languages. Clang is a CUDA compiler. Clang is a HIP compiler. Clang is an OpenMP compiler in and of itself, even off-the-shelf Clang. Clang is an OpenACC compiler. So those things are just, this is my input code written in these programming models, and I can just pipe it into Clang, and Clang knows what to do. But right now, if you pipe CUDA into Clang, Clang doesn't emit, LLVM IR, like it emits LLVM IR, but not with OpenMP runtime calls, but with CUDA runtime calls. And what I'm saying is, we did a proof of concept that shows you can get rid of the CUDA runtime calls and instead replace them with OpenMP runtime calls, and then it becomes portable. And that's kind of the motivation here. It becomes portable and becomes interoperable. And now the question: how much is coding? How much code do you generate versus runtime calls? That's a question for the ages. You can go either way. You can make a runtime call for effectively all of the high-level features, and then just say, "Oh, parallel. Here's the body. Like here's code for the body. Parallel, and the user gave these clauses, and let everything be handled in the runtime." Doable. You can do the opposite of that. The runtime call is really just very low level, and you emit all of the compute logic directly as inside of Clang. Historically, for OpenMP at least, it was further on the side of generating a lot of the logic directly with Clang. And we're currently pulling it back, at least on the GPU side, to have more inside the runtime, more higher level calls. That being said, on the GPU side, we actually link the runtime into the application later again, inline and fold everything together, and we'll see that later. So while we do that, we mostly do that to simplify code generation and simplify updating and maintaining all of this stuff, because now we can actually write it in C++ in the runtime, and that is easier than writing Clang C++ that generates the stuff. So we just, I mean, there's pros and cons. There's no clear answer to it. And maintenance argues go more into put it into the runtime. Has benefits, has drawbacks though, but yeah. Makes sense? Okay. Oh yeah. Now I have a couple of user developer sites. So these are interesting things for some users and hopefully developers. And when I say developers, I mean developers of OpenMP and LLVM, more like compilers and tooling and so on and so forth. So when I talk to people and people come to me and say that doesn't work or performance is not good and so on, and they don't use a build from last week from LLVM upstream, but they use anything older, I'm like, is it still reproducible last week or today? Because especially on the OpenMP front, we just don't have the resources to support too much. So it's moving so fast. Stick with upstream, update every week. Don't get stuck on any release version for any kind of development you do. Believe me, you'll thank me in 3 years. It's work to rebase once a week or once a day, but the work accumulated to do that is not as much as rebasing every year, every 3 years, and you actually benefit from it a lot. Compiler remarks, we'll see some later on. If you're a user, you should certainly read up on them. And then we have like information, especially on the offloading side. We have things like libmcarbit info that tells you, how did I offload stuff? When did I copy things? Why did I copy things? How did I run kernels, and so on and so forth? Like, a lot of good information is in there. It's a bit set, so you have to read up on what information you can get out of there. Similarly, we have libmcarbit profile, where you can just get a Chrome tracing file with just one environment variable. It's not going to be super great, but for the first shot, what's going on? Is there some, immediately red flag? Super easy, it's built in. libmcarbit debug is a two-way option. So you have the environment variable, but you also need to set the command line option, because otherwise it would be costly. And we use these two together to make it free if you don't use it. And if you use it, it's costly, or potentially costly, let's put it there. And you can enable like runtime assertions in the GPU runtime. Otherwise, the assertions are just disabled and stuff. And then you have a lot of assumptions. So the standard in every programming language says, this is the semantics. Somebody thought about that and said, this makes sense. But a lot of times the semantics is generic. And as a compiler, we would like to say, everyone uses it this way. And if I knew you use it this way, I could do something cool. But semantics allows you to use it a different way. Nobody does that, but it's allowed. And I cannot break code. And I mean, there's compilers that just, ship ways that will break code, but I don't. So we have flags in environment variables that say, hey, compiler, I promise you I don't do this, that. And they have explanations, and they kind of tell you what they mean. But with those, you can help us, optimize your code better. And again, offload LTO, device side LTO. It will be default soon, but it's really good. Okay, these are, again, take a look later. A lot of ways to reach out to us. We have even in the OpenMP world, we have a Slack and so on, LLVM OpenMP world. We have a Slack and so on and so forth, various meetings. And why do you want to reach out? This is a result from OpenMC. They reached out to us, and they had really bad performance on GPUs with OpenMP offload. And those are factors. So you multiply them all together. And that is after, 2 or 3 weeks that we worked with them and looked with them through their code and their stuff. So they got 100x speed up, and that enabled them to actually start working on their stuff. And the rest they got through, doing it alone. So reach out. We're interested in what people do in applications and so forth. And we want these things to, work in real life. And we fixed our compiler because it was broken. Effectively, there was a performance bug, and we found it with that app, and then we're like, yeah, I'll go and fix it, and then you get an 8x speed up, and they were happy, right? And then you see Intel showing the results of that OpenMP offload compiler at ISC, making a big slash that they're like so much better. I don't care about the numbers, but the point is, OpenMP offload is working in production, portable, and performant. Oh yeah. Again, paper thing. So for everyone that is here, not a user, but a developer, potentially a PhD student, and so on and so forth, we publish. We work on upstream LLVM. We put our code in there. We work with applications, and we publish. So if you are interested, you can work with us. We put papers everywhere, like good, bad workshops, conferences. It depends on what you're interested in. And it's not like, oh, I can either do research or I can do LLVM upstream development. You can do both. Might be harder, but it also has benefits, believe me. Okay, let's do some not OpenMP for a second. AI, everyone. Why is it? Oh my God. Anyway, sorry. That was not supposed to look like that. It was supposed to look like that. So AI, everyone wants to do AI. Everyone has to do AI effectively. You have to put AI in any proposal that you write, or ML or whatever. So we did a little bit of AI. We actually do various things at the same time. We work with Google people and so on. But this was something we had Google Summer of Code students working with us too, Diretto and Torindo. And what we did is kind of two different projects. We continue them now. The first one is a model that effectively looked at a piece of code and decided for the next 5 passes in the LLVM optimization pipeline, should I run them or not? If the model said, don't run them, you just don't run them, you save compile time. You might lose out on optimizations because you didn't run passes that are supposed to make things better. But the fun part is you can put different thresholds in there, and then you can, like, depending on where you are, like, is compile time important for you or not, or is like performance important or not? You can exchange 2.7% compile time for 0.1% execution time. So it gets a little bit slower, but you also save a reasonable amount of compile time, and then you can do different thresholds. And this is far from perfect. So this was a Google Summer of Code project. We know there's various things that we can improve, and we're looking at that now. But there is potential in using AI for heuristics like that. On the right, we did something similar. Look at functions in your file. Look at functions in LLVM IR and decide if they will benefit from different optimizations. So the idea is that there's different optimization levels. So 1 or 2 or 3 are the most popular ones, right? A lot of the functions, we can basically cluster them, and then we can see that there's certain clusters here, like these guys here. Like, we clustered them based on certain characteristics of the function. And for those guys, if they fall into these clusters, we don't have to run O3, because O2 and O3 generate the same code, they perform the same. So we basically checked it after the fact. So we basically can say, we could look at an IR and say, oh, you don't actually have to run this, like O3 on this function, just go to O1, where you, for example, are in this cluster here, you could think about it, or in this one, or go to O2 for almost all of them. Only these two have codes that benefit from O3. And again, this was just Google Summer of Code work. There's a lot more to be done. Oh yeah. I have like who is interested in GPUs?
Everyone.
Okay, cool. So I have a little bit of GPU stuff. I'm running out of time. I see that. So I'll try to go fast through this. This is what LLVM OpenMP op does to make OpenMP run fast on GPUs. And the base problem for you to understand is OpenMP comes from the CPU world, where there is sequential execution, and then you have a parallel region. You spawn some, like you activate some threads out of nowhere, and then you execute something, and then those threads go away, and then you have sequential execution. If you think about CUDA, that is not how it works. In CUDA, there is a lot of threads, and then you do something with them all the time. Even if you want sequential, you manually say, oh, everyone, wait for a second, I do something sequential, right? So it's completely different mindset. And things like the stack on a GPU cannot be shared. Stack cannot be shared between threads. On a CPU, absolutely. So there is conceptually execution model differences. And let's take a look at this. So, CUDA kernel launch, everyone executes the function. That's SPMD mode, right? By the book. And OpenMP, this basically tells you only one thread does this, then all the threads do this, and one thread does that. So now you have this very more complicated picture here. And that is still how not everyone writes OpenMP like that, but we have to support this. And some people do write it like that. And there's a good reason to do so, don't get me wrong. Now, what do you do with the threads in those empty areas, right? You have to kind of keep them busy. I mean, they don't go away. On the host, it's a different story, but on the GPU, that's actually a problem. So they exist, so you have to do something with them. And in LLVM OpenMP, if you look at our terminology, our runtime, our documentation, we call this SPMD mode. Everyone does the same. We call this generic mode, there is a mechanism to make threads do nothing, like to keep them away or hide them or whatever. How do we do that? So one more thing. You have to be careful what you do here, because if inside this, you could think, oh, I could just, do the same as I do in CUDA, right? Where you do if thread ID equals 0, then execute the code sequentially, barrier, and so on and so forth. That's the first thing you come up with. Sounds great. Sounds great. Problem is, what if in the sequential parts that you may or may not see are things like another parallel, and now you want to use threads in there, but your threads are currently waiting at this barrier. How do you get them back? I mean, technically you can do all of those things, but you start to see that's a problem. Similarly, what happens if in this parallel region there is a barrier? Now OpenMP says everyone has to hit that barrier, but only one thread is supposed to be active there. So now you have, like, again, a clash between your implementation and the model. And I mean, you can make all of this work, but you see there's a lot of problems here. And what we do instead, well, not what we do instead, but technically what we do is, since version 14, we allow this generic code to be SPM designed, so made into SPMD code. And we kind of deal with those things. At least we detect that those exist, and we have analysis and transformations for all of that. Let's take a look at how generic mode is implemented. So initially, and at the very beginning of a kernel, we split the threads into a main thread and the rest. The rest goes into this node over there, where they effectively wait. As soon as the main thread hits a parallel, it will tell them the others, the workers, this is the parallel I just hit. I need your help to execute it. And then they will execute it. And then they will tell the main thread, hey, we are done. And then they go back into the wait state. So this is what we call the generic state machine, which is just two states. Like, I'm waiting for work, and I'm done with my work, and then I decide if there's one more state. Technically, you get a signal that you should, exit. Like, you are done, the program is over. And then they signal back to the main thread, we're done with the parallel region, and the main thread continues execution. Now, how do you tell the workers what the parallel region is you just hit? Because the parallel region might be in a library, in a different translation unit. How do you identify a parallel region that your main thread just hit, right? You could, inside of your target region, inside of your kernel, you could call into a library. That library has a parallel region. How do you have a name for that, a handle? You haven't even seen it when you started the kernel. You know where it exists. So what we do is we use function pointers. Okay, function pointers are great, but if you ever talk to a compiler person, as soon as you take the address of a function, you take a function pointer, the compiler gets a little skittish. Compilers don't like that. Taking the address of things ain't cool. Because taking the address of things makes things possible that we don't like to happen, and we are very careful at optimizing around that. And it's not only function pointers, it's also addresses of globals and stuff, but function pointers especially. So, okay, this is all what I said. So what we have an optimization that tries to replace this function pointer with a unique ID instead. And I'm going to skip over most of this. Why? Because if you have a unique ID, it's not a function pointer anymore. And then that function, and then you just don't. Sorry. Here you just call the function pointer that is given to you, which is an indirect call. And here, if you can do this unique ID trick, you can also specialize the call sites and make them direct call sites to the actual functions. And then and you do that again. LTO for offload is a thing, because then you see all of the code, and we can do all of these funny things interprocedurally across all your libraries, across all your kernels. Yeah. If you want to know if the compiler did something good with your stuff, use the optimization remarks. The OpenMP opt has optimization remarks for things it did, things it couldn't do, and analysis remarks. And we have a web page explaining them. Use that. And if there's, if your explanation is not good, or you want to, know more things, reach out. We can add more stuff. So how is all of this OpenMP opt stuff implemented? So when we started, so there was two options. One is everyone says, yeah, you can inline. Inlining is great because you inline everything, and then everything is in one function, and you can easily reason about it. But parallelism has this level of abstraction. Think of pthreads create. You pass the function pointer to pthread create, and you can't inline that because the call of that function pointer by the threads is inside the library. Every parallelism looks like that. It doesn't matter where you come from. It's always, here's kind of a function pointer thingy, and then I call some, magic code, library, assembly, whatever, and there is no inlining. You can't inline that because it's conceptually a different thread. So what we did instead, we said, okay, inlining is not an option. What is the alternative to inlining? Interprocedural optimization. So we said, let's do interprocedural optimization. The present in LLVM was really bleak. So we decided to build a new thing for interprocedural optimizing LLVM. It's upstream. It's used by OpenMP and the AMD GPU backend, but not by many more else for reasons that we can discuss later. So the thing is called so one other reason why this is useful, we did a study where we compared thin LTO, which is effectively a form of link time optimization where you allow functions from one translation units to be inlined into functions from other translation units. And we compared that to HTO, which is header time optimization, which effectively just annotates the functions with their properties. For example, this function only reads memory, or this function will write memory through this pointer and read memory through that pointer. And then we compare it to performance. And it turns out that a lot of the benchmarks actually perform the same if you only have abstract information about the function as if you would inline them. Only there's a few here. There's a few benchmarks here where inlining actually gives you a huge speed up that you can't get by just having kind of function summaries, like things to know about the function. Why is that so? Mostly function pointers again, because there's no way to reason about that. And very small functions in hot loop, stuff like that, where just the pure call overhead is the problem, not actually knowing anything. But oftentimes the problem is there's a function call and you don't know what to call. So you assume the worst, and then optimizations stop working, and that's the problem. So if you have information about the functions, you actually you don't have to do inlining. So right now we are heavily reliant on inlining, and you can, what I want to have the option to be not always inlining dependent, but I want to do function specialization and interprocedural optimization and have the entire space for the user to explore. So the user says, I want to do inlining, great. I want to do no inlining, also great. Then you just happen to be on the line below here. And right now you can't really say that without being, totally screwed.
I mean, you talked a lot about inlining, and obviously with the code bases you work with, inlining is a big issue. But isn't this, I mean, this obsession about inlining, isn't this a language-specific dead end? I mean, in C++, everything kind of is implemented by means of name mangling and generating functions. And then you need to get the stuff back in because you have those tiny functions. But if you write sane code, you don't have this issue. Yeah, it's
even in Fortran you have that issue.
In C++, you would call it.
No, it's just less, but the issue exists.
Yeah, but honestly, I mean, function call overhead, if you pass arguments by registers, which you have in most architectures nowadays, it's probably a couple of cycles. So if you do anything in the function, it will make up for the function overhead.
I have an example where we annotated in one of the proxy apps for nuclear reactor simulations, one of the proxy apps for OpenMC. We annotated one of their complex math functions that just took 2-3 complex numbers and did some math on them. And that was in a different translation unit, so an opaque call inside of a hot loop. As we annotated it, it was not only that it could, it wasn't about inlining, but we annotated it. And what happened is the compiler just moved this call out of the loop. Now you get complexity reduction. So instead of calling n times, you call once. Here we go. And that is, you can get that with inlining as well. But the point is, any sort of call is inherently an optimization barrier. The question is, how much of it is it? And how much does it cost you? And even the Fortran runtime library is full of calls. Nobody actually in their sane mind generates all of that in the Fortran compiler code generation into your application. That's just bonkers, because we go back to the maintenance argument. So at some point you have the choice of annotating that properly or inlining it. Pick your poison. And I mean, there is no correct answer to any of this, but there's always a scale of where are you and where do you want to be. And
yeah, maybe we are on a special island, yeah? Where those kind of problems don't exist.
Okay, I'm running out of time. So I'll finish here. So with this topic thing. So attributor is what we build. And if you look at LLVM IR, the LLVM code, you'll find it. It's a framework to do interprocedural fixed point iteration. And it has a lot of built-in features that are helpful for people to use. So generally what it does is you say, I want to know these kind of informations for these points. So I want to know what the alignment is of this pointer. I also want to know if this function reads or writes memory. And I want to know if these two things alias. So you see a couple of things you want to know. And then you, let's say, tell a thing run. And the thing starts running. And at some point it says, I'm done. And then you can look at the things and say, okay, what are the answers to my questions I asked you earlier? Do these things alias? Yay or nay? What memory is accessed here? This kind of memory, and so on. So it gives you answers after it read, right? And then it can also put those answers into the IR, like basically transform the IR if possible. So you can ask the questions for all these kind of positions, function return arguments or arguments, whatever details you find that online, and it works through fixed point iteration with some states. We'll skip that. This is a very old slide. This tells you what kind of abstract attributes, things that you can ask. It already supports. It supports more nowadays, but you get the idea. You can ask, is this store dead? Is this function dead? Is this call dead? Is this load dead? Can I delete effectively? You can ask, does this function potentially unwind my stack? Might this function recurse? Will this function return for sure? What memory locations are you accessing? Can I privatize a pointer? So passing a pointer to a function, can I instead pass the values of that, like the values of the thing? What threads execute what, like execute this? All threads executing this together, kind of in an aligned fashion, or is it only the main thread executing this, or is it, don't know. Dominance, assumption infos, pointer info. How is this struct used? Who stores into this struct? What is stored into this struct? What will this load? And all of that is kind of interconnected. And what it does for you is, if you ask a query through the API or through any of those, they look through they deal with weird things in the IR and they look through stuff. So it's like, if you ask, what is the value of the return value of this function? And if the return value of that function is, for example, a load, it will automatically check what is the value of that load. And then we'll check, okay, what's the pointer pointing to? What is the object there? Can I reason about that object? Is that object local enough that I can reason about that object? Or is that object, open to the world such that anyone could do with it? And it knows about things like synchronization effects, such that even if it's open, but there's no synchronization between certain points, I can still reason about it, because it would be a race if somebody would write it. So I can still reason about it. So it knows all of these things. You don't have to worry about that. You can just use that. And what you get out of it is, this is all the stuff it looks through: memory, calls, find nodes, selects, all of it. It's kind of nice. And then if you can dump the graph of what uses what, and then really everything uses is this code dead, is this function dead, and so on, because it's sparse. It's like, if you think sparse conditional constant propagation, everything starts by everything is dead. And then it updates stuff. And then that uses, does this pointer capture? What are the potential values for this pointer? Is there a constant range you can give me for that thing? What are simplified values for this pointer? Is the memory location read or written? And in what memory locations are read or written? And stuff like that. And so it's super powerful. It's not perfect, but we use it in production. And I think I'll stop here because we're running out of time and I want to have some questions. There is going to be another talk tomorrow, so I'll have some more opportunity to talk about things. I actually wanted to let me go to one thing in the end here. So there's not only OpenMP, right? I have a couple of these not OpenMP slides. This is a study we did a few years ago for ISC, where we tried to determine if the compiler knew more about your program. Don't read all of it. Listen to me. If the compiler knew more about your program, so if it knew the alignment of all the pointers, if it knew that all the functions are read-only and so on and so forth, like const and whatever, pure, what performance could you get? That question alone, like what is the potential performance you could get with a certain code on a certain input on a certain, nobody could answer that to me. I mean, like, is what I get good, bad, somewhere in between, and where in between? And on like proxy apps we care about, we get like 20% speed up. And most of the time it's like 1 or 2, 3 different decisions. And we tried out, tens of thousands. And most of them are, irrelevant. They don't actually change anything. So we add that information and it doesn't change a thing. So adding information manually is not a good idea, because 95% of all the information you add manually, like restrict, const, pure, it's trivial. It doesn't matter. So to really manually doing things is not a good way forward. And after that, we did the Oracle stuff, which is the same idea, but this time with alias information. What if everyone and their cousin tells me alias information is a problem, especially in C, C++, right? Everyone says that. Anyone has any proof for that? Anyone ever seen proof, like actual proof? I mean, this is just a measurements, but it turns out that, C++ with OpenMP, with Cocos and CUDA, Fortran, OpenMP offload, tasking, MPI, having perfect alias information gets you something, but not as much as people make it out to be. And this is really having perfect alias information with LLVM. Now, you can argue, oh, then LLVM doesn't use it all right. Fair. And that's probably true. And this has different reasons, chicken and egg problems again, and other things. But point is, we need to build these things that help us map the space of where we are in, because we're aimlessly trying to optimize stuff. And we have no idea, like, what is the headroom and where is actually the big bang for the buck. So let's start looking at that first, building tools that help us, map out where we are and where we could go. And yeah, I hope that was some informative information.
Either GNU compiler?
Sorry?
Either GNU compiler.
No, this is LLVM Clang. All of it. I mean, yeah. Why?
The previous slide you were talking that, for example, aliasing is important, is not important, but it makes a difference for the legacy compiler.
I mean, it might. I mean, that's fair, but for LLVM on these benchmarks, in these configurations, this is the difference we observe. I mean, I'm not saying anything about GCC, but I'm saying that at least for LLVM, if you invest your time in building a better alias analysis for LLVM and you care about these codes, you're not going to get much.
Yeah, but it depends. Does the compiler still do its stuff on a best effort basis without perfect aliasing information? And if you provide this information, I mean, it doesn't hurt. So why you shouldn't?
I mean, what we did is this wasn't it doesn't hurt. I mean, it has some cost to it either way. Either there is the manual cost of writing restrict everywhere and maintaining it and making sure it's correct. And then there is what we did is, this is not even proven correct. This is just on a certain input, the results are the same. It's all what we can say. So this is not for production use. This is on the certain input. What can you get? And I mean, this is costly to generate, but that's a different story. The point is, this is to map out the headroom.
I mean, you could always globally rule out aliasing.
Oh,
yeah.
I don't have the numbers in my head, but I think like half of them, that will work. That will work and the tests will all pass. For the other half, it won't. The tests will fail.
Really?
Yes.
So people build stuff relying on aliasing. That's
standard vector relies on aliasing.
Okay.
if you say standard vector doesn't alias, standard vector has 2 pointers as elements, an end and a begin pointer. And if you say nothing aliases, you'll break.
Yeah, okay.
And that's just the first example that comes to mind. If you say nothing aliases, you'll break. In enough cases that you can't do it. The Intel compiler has a switch to say exactly that. I mean, if it works for you, it works for you. I'm not telling you not to use it. It's up to you. But for half these codes, we couldn't, or I don't know if half. I can look it up. I know we know. and that was the first thing we tried. We basically, our thingy said nothing aliases, and then if all the tests passed, we said, yeah, okay, cool. What is the performance now? And then if not, we ruled out, and then we know how many pessimistic queries we have to answer. We have the numbers, and it's not many, obviously, but there are some, right?
Thanks a lot. Any questions? Any questions here from the room?
Probably the slide itself. Probably you want another reason why you have the speed down with the 7%.
Oh, which I mean, especially on GPUs, any wrong, like any choice might be wrong. I had programs that forcing inlining on all the GPU code basically gave you 30% speed up against the inliner heuristic, and I had other cases where I got 20% slowdown. GPUs are still very sensitive on resource usage, so having too many instructions and they could even be like secondary effects, like you did something beneficial, but then because of that, the register allocator got a little confused because the pattern wasn't recognized, and it's unclear. I can't tell you for sure, but things are finicky, and our optimizations are all local, and they're also. The optimization function is not rooted in reality. So what compilers do is not optimization in the classical sense. It's more of a local transformation and hoping for the best thing.
I'm kind of wondering, is the manufacturer actually leading the development of OpenMP GPU offloading, or is the LLVM team actually doing that?
Yeah, so the question was if the vendors are leading the OpenMP offloading development, or if LLVM is doing that. Let me go to the very beginning. I had this slide about what we do in LLVM OpenMP offload, and it's a bit of both. So we have weekly meetings with vendors. So that guy here, 25 people. It's mostly GPU focused. Yeah. All the vendors are there. We're there. Academics are there. Everyone that kind of works in LLVM OpenMP. I'm the code owner, gatekeeper, if you want. And the community does a lot of the direction planning. The vendors help out with their hardware support, and they help out with other things, and they sometimes also drive things. So, but the community is leading in a large degree. And most vendors, not all. So different vendors use community code to different degrees. AMD uses pretty much all of it with some additions that they made. Intel uses pretty much all of it though we don't support Intel hardware, so they roll their own there. But they still support a lot, like to take a lot of the other stuff. HPE, for example, only uses the front end with us and rolls their own runtime, but they use the same API, so they're API compatible. So it depends on what vendor you talk about.
Okay, so I guess I'm trying to say AMD because several weeks ago or 2 months ago, I tried to report a project that works in Monte Carlo ray tracing to Ruby, and GPU OpenMP uploading doesn't really work. I raised this issue to their support team, and they told me that during their bi-weekly meeting with the manufacturer, there seems to be some issue with C++ class encapsulation that couldn't be easily solved. At least it's not being supported like as well as like the ones on NVIDIA GPUs.
Okay.
Yeah, so I'm kind of curious if it's better for me to maybe bring up this issue to the LLVM team
I mean, I would say yes. I would also say build your own LLVM or float compiler on Lumi, though there are some. You can actually use some of other people, or you build your own. It's not that hard. And try it out again. Use the tools that we have to get information about the optimization remarks, what happened, what didn't happen, why. It also gives you information about what to do. Use our info tools to see what is, how we execute stuff. And then if the performance is not as, or no matter what the performance is, feel free to reach out and, we discuss the results, and we also help you figure out what's going on. We work with the Cocos team doing the same right now on different Cocos applications.
Yeah, so I actually encountered a Clang crash, well, the Clang simply crashed, and it reported it encountered some sort of EAG issues. So is that kind of a software issue, or?
I mean, if Clang crashes, that is always a bug. If it crashes in upstream Clang, file a bug on GitHub issues. And if it's an OpenMP problem, tag the OpenMP, at the OpenMP tag, we actually actively monitor our bugs.
Okay, thank you.
And we report usually, we at least comment within a few days, and oftentimes in a few days it's fixed.
Okay.
I have a question. Sorry.
Slightly technically question probably. So with respect to the CUDA or general GPU uploading, your example was one CUDA block with 4 CUDA threads, and which of course makes things a little simpler.
Yeah.
But I would imagine that if you had more blocks and especially more threads than fit into a warp, you would get issues with this kind of busy waiting of some of the threads, because that could effectively clock NSM, or between blocks you would even need to have some sort of synchronization mechanism there.
Right. So
is this a problem?
OpenMP defined teams to be effectively mappable to thread blocks, such that between teams you don't get synchronization, such that we can map them to thread blocks. So one OpenMP team is one thread blocks. Now, how do we split? We actually don't split up the main thread into workers like this, the way I show it. The main thread is in its own warp.
I see.
At the very end, in it by itself. All the other threads in that warp we just exit, and then we have one warp for main, and the others are workers, which simplifies a lot of the problems you just mentioned. It's all doable. Technically, it would also be doable to do it like differently the way I show it here. Even you can actually do it. It's just it's usually going to be slower. But yeah, so there are problems, but most of them can be solved by the way OpenMP was defined and playing real tricks with where you place stuff. And then technically the main thread exists twice. So we don't actually use this main thread that executes the sequential parts to execute the parallel parts. But there is another thread that in the parallel regions assumes the identity of the main thread, just says I'm 0 now. So there's 2 threads that pretend to be the main thread, just to make all of these things simpler.
Yeah, but that makes sense for performance reasons anyway, right? But do you spawn actually new threads, or do you keep them in a sort of waiting?
Yep, they are in the state machine, waiting for effectively async threads. So they're just waiting in async threads, and then once the main thread hits async threads, they get all activated.
Okay, so
and we use get memory to communicate between them. Yep.
Okay, makes sense. Thank you.
You had a question?
Yes. You told about the OpenMP IR builder.
Yeah.
And that you can use it with any language, even one you've made up yourself.
Yeah.
How would that look like in practice? I mean, I don't have a Pragma OMP parallel in my XYZ language.
Yeah.
So how would I use it?
So the OpenMP IR builder effectively exposes that kind of interface, Pragma OMP. Like it says, create parallel region, and then it takes a couple of, the arguments effectively match the clauses of a parallel, and it takes one argument that is a callback to build the body of the parallel. And when I say build, it could be as simple as, here's the IR for the parallel, just make a branch to it, and then I build the body. And so from your language, you would, as of right now, you would kind of need to map your parallelism to this conceptual OpenMP parallelism. That being said, we are open to exposing or making the interface more general. I don't think they're too rigid right now, but we're happy to expose more generic interfaces on that level and even in the runtime. So we already added extensions to support OpenACC features, and the whole other languages use it. Some people at Chapel started, like at HPE with Chapel, started to looking into that, using it for offloading. Some people played around on the Rust side with using that for parallelism and so on. We had the Python OpenMP folks that added pragmas, but I mean, that was just pattern match this string and then call OpenMP builder in their, LLVM light implementation and so on and so forth. So it allows you to say, to not care about the fact what runtime calls we issue to make parallelism happen. You can just say, I have a function here and I want that many threads execute that function. Go for it. And that's kind of nice. And similarly, you can then say, I have a task here is a function that is a task, and I have these dependencies, make that happen. And you don't have to care about all of the low-level details. Again, I think the interfaces are good, but we're happy to adjust when people come and say it's not good. And that is, in general, people should consider that LLVM is oftentimes we change things if they're not good, if people need different things. They have use cases and can argue, hey, this is bad and could be better. So a lot of people are discouraged by, oh, it doesn't work out of the box, or that interface is missing this one parameter, so I can't use it. So I rather roll my own entire thing downstream. And I'm like, instead of adding this one thing upstream, and you made yourself a lot of work and maintenance work in the future. Why? You add that one thing upstream, and then you benefit from all the improvements there as well. So building things on top of each other is good, even for researchers, in my opinion.
So one question, you mentioned that most vendor compilers now use LLVM as their base. I mean,
Yeah.
Intel, we know, also now switched kind of.
Yeah.
What about NVIDIA? I mean, especially in your domain, NVIDIA is kind of a monopolist, you could say. So what's the relation between the NVIDIA toolchain and LLVM? I mean, they have PGI, I don't know. Maybe they already use LLVM, I don't know. But...
So there's a couple of answers to this, especially because they have PGI. NVCC is LLVM based. Initially forked 3.7 or 3.9 back in the day. Updated it. The last I heard was LLVM 7, and they're constantly rebasing, but it takes them a year, 2 or 3 to rebase. So they're always year 2 or 3 behind, at least. But the NVCC is LLVM based. They're going to roll Clang as a new Fortran compiler. So they're all in, the PGI and NVIDIA folks, to use Clang as their Fortran compiler with some downstream stuff. PGI's compiler is, let me put it like that, sooner or later going to use Clang as a front end, at least, because they cannot do anything else.
So they just do the back end as a...
I didn't say that they will continue using their own backend. They may or may not. I don't know, but they will have to use Clang as a front end eventually. And that's in the cards. I mean, they use already Clang on that part on the Fortran side. It would be unwise not to buy into that, and they might actually go the MLIR route with C++ as well, because they seem to be very interested in that. But let's summarize: a half or 3/4 of NVIDIA's toolchains is LLVM based already today.
Okay, but the critical, or I would say the back end or the code generation is still proprietary, their
Yes.
own stuff.
The NVPTX backend that we have in LLVM is provided by Google and effectively maintained by Google.
Okay.
Also, Clang's CUDA support, the fact that Clang is an actual CUDA compiler, is because of Google and maintained by Google.
Okay.
Now we can talk about why that is later. But yeah, that's open knowledge. That's you can just read that out.
Maybe one last story, but one last question.
Go for it.
About relevance. So in our domain, it's a bit, yeah, we don't see many large scale codes using OpenMP offloading. Do you have references? Because I mean, programming is about looking at other code, mostly, I would say, at least for me. So do you have some references of large production codes that are where I can get the code which use OpenMP offloading?
There's 2 science codes that use OpenMP offloading right now. There's others that are looking into it, and there's going to be more as soon as Clang is up and running. but there's 2 C++ codes that bought into OpenMP offloading as their programming model early on. And those are power users that we work with a lot that helped us, you know, find bugs, even fix bugs, fix performance bugs. And one is OpenMC. It's open. You can go on GitHub. That's the one that Intel provided the numbers for. And Intel also provided the numbers for QMCpack, which is the other one. Now, to what degree you call them like you know, production, that's not for me to decide, but they are part of the ECP apps. So there is a pre-selection towards something important, and they're reasonably big and complex. So, and it apparently do some stuff that is important because I don't understand it. So 2 codes are out there. I think there's more to follow. And at the very beginning, I kind of tried to make the point, I don't actually need people to write OpenMP offloading. I don't need people to write pragma. What we're building, most of our time is in these runtimes and tool chains and tooling and optimizations. And that is on a level, there is no pragmas anymore. And we have this proof of concept where we map CUDA on top of that, and so on and so forth, where it's really like the syntax wars are pointless. You write whatever front-end syntax language you think is best for you, for whatever reasons you come up with that. But on my level, we are going to unify all of that, and we're making them interoperable and working together, and actually cross-language optimizations are happening already. And that works. You can combine CUDA code with OpenMP offloading right now in LLVM Clang. And we're building right now, and that is one of those things that I didn't show, is like an OpenMP kernel language extension, like first proof of concept, and then we try to standardize that, where it's really, what if you can replace all of your CUDA code one-to-one, really alpha renaming HIP style, with something that is OpenMP, but then in addition to being HIP, like the idea of HIP just being one-to-one replacement, it also is compatible with all your other OpenMP. Your tasking on the host, your task depend, and on all of that will still work. It will work together. You can decide, oh, I just do target teams distribute parallel for, or just target loop on some of them because I don't really care about the last ounce of performance. But on others, I really have to go down and write, you know, a portable shuffle and a portable sync threads, and then you get sync threads and shuffle, but they're portable across all the architectures. And you can now have the full spectrum of, I just do omp loop and the compiler will take care of me. I do omp teams distribute parallel loop and it will do what it does. Or I take control of myself and I write low-level CUDA code just with, you know, instead of CUDA, it says omp X or omp later. And all of it works together in the same app. It's even the same application. It's the same thing.
Okay, so thanks again for a wonderful talk, and goodbye.
Thanks for having me.